uh, and we would like to understand certain things like scalar matrix we discussed. Now let us look at if when A is equal to B, right? When all the elements, the corresponding elements of two matrices are same, then only A is equal to B. Just because the matrix magnitude is same, it is not correct. The order of all the elements should be same. Then only it will be equal. So that's one property that we would like to check. The second property is, how do I add? Addition is very simple, right? The third matrix which is created out of these two will be added with the relevant matrix, the equivalent cell. They will be added and they will be given here. Same thing for subtraction. Hadamard multiplication is same thing, but matrix cross product is different. Matrix dot product is different, right? We will see how exactly we get that, right? In fact, when we do this, some of the matrix operations you can add 0, nothing changes, right? Scalar multiplication is possible, right? We can go for scalar multiplication, right? Properties you can check because like he was discussing in the morning, I changed the rows and I did all those things. It's only alignment is different, but the structure remains same. Replacing the rows or columns, that's the beauty of will 2x plus 3y is equal to 5 change when I make it as 5y plus 3x is equal to 10. Is it going to change? 2x plus 3y equal to 10, 3y plus 2x equal to 10, right? I have changed them. Now I have x plus y is equal to 5, y plus x is equal to 6. Now I will make it as x plus y is equal to 6, y plus x is equal to 5. Is it going to change? I have changed the rows, I have changed the columns. The properties are not going to change for the matrices. And same thing in our linear algebra. I mean just algebra. When we try to solve multiple equations, same property holds true. And those properties we need not have to check, do all those things because the library builders might have done all those things. Why we should do and we should say yes, I have also seen. Right. Normally it has been told to us, you must prove, you must do. No, for me, I'm an application engineer. I'm not algorithm developer. I'm not a mathematician, things like that. We are pure application developers. If it is not there, I should know enough algebra to develop a particular thing, not beyond that. To prove this matrix works and all those things is not necessary. Inverse, I will not check whether the determinant is 0 and or not. Simply, I will call P inverse. If it is there, give me inverse. If it is not there, give me pseudo inverse. I will not look at anything. Technically, 20% what is required to solve 80% of the problems, we will go with that. If you learn that much, safer. Don't try to optimize anything first time. Second or third time, you have to optimize. First time, things should be working. Let that be working. Then we will see. Right? So once it has been done, so A into B, B into A, if it had to happen, right, they must be of same size. In fact, when we look at 2 into 1, 4 into 2, it is not possible. 2 into 1 can be multiplied with 1 into 4. 1 column, 4 rows, right? 2 rows, 1 column, it is possible. Right? But the other way it is not possible. Right? For example, 6 into 2, 16 into 3 is not possible. 6 into 2, 2 into 6 is possible. Right? 3 into 3, 3 into 3 is possible. 3 into 3, 1 into 3 is possible. That is the reason when we go for these type of things, when we say 1, 2, 2, 3, 4, 5, right? This will be 3 into 2, right? Another one we will have as 0, 1, 2, right? I cannot do any multiplication here. Rather, I would like to make it as 0, 1, 2. So this becomes 3 into 2, 1 into 3. I can multiply. So we have to convert all those things. Those properties we don't check. 1 minute. Paper linear 2 million, 2 million paper linear. Sorry. Okay, now let us look at some of the matrix operations, right? When you multiply, there's a possibility that I can go for, if I go for 2 by 3 or 3 by 2, 3 columns and 2, and 2 columns and 3, we will get 2 by 2. So how do we get this? Basically, we multiply, add all of them and put them there, right? So we will use these things and get some of these operations up and running. Then we will look at identity matrix, right? Then transpose of a matrix. Transpose of a matrix, though all other things are good, right? We would like to look at where do we use matrix operations. For example, I want to do addition. Where do you use that? Normally, we want to obfuscate the code or obfuscate the data. We try to use the matrix operations. For example, just add 5 to everything, right? Divided by maximum, then the total changes. Right, 1 by 2 is different from 1 plus 5 by 2. Isn't it? If the maximum value is 2 or 7 or whatever it is. Now let us say that maximum value in that column is 2. Right? Now 1 plus 5 is 6. 6 by 2 is 3. I may not do divide by 2, or I may go for even 2 is taken plus 5. It becomes 6 by 7. It will not be 1 by 2. Now if you see, I have 1 by 2. This is my column matrix. 1, 1, 2. What is the maximum value here? 2. Now I would like to go for 5, 5, 5. What happens here? 6, 6, 7. Now let us get the standardized value for this or normalized value for this. Divide by maximum, right? 2 is the maximum. Divide it by 2, it will be 0.5. It will be 0.5. It will be 1.0. Now look at this. It is 6 by 7. Right? 6 by 7 is 0.566. 0.566. Right? This will be 1.0. I can change it. Right? Now this looks totally different. So this is obfuscation. Right? Now if I want to share my data, I will share this data. Unless he knows what the operation I carried out, he cannot recreate the data. Right? Normally in Kaggle and other computation, they try to give this type of data. They will not give this data. Because if this data is given, it is very easy for us to find who is that. Even if without number, without name, without identification, we can correlate that. Right? So because of that, this is one of the operations. One operation. Second operation. This is a point in space. Right? Now let us take XYZ. Right? 1, 1, 2 point is here. When you add 5 to this, what happens? It is more translation, right? It is a translation operation. A vector is translated, right? So translation, obfuscation for multiple applications, we try to use the addition. Same thing with subtraction, addition or subtraction, we can go with that, right? So transpose is very important. Transpose is nothing but pivoting it. Hold at one point, pin it, rest of the things rotate, right? So whatever is the row, 1, 2, 2, 2, 2, this will become 1, 2, 2, 2. Can you see this 1, 2 become 1, 2, 2, 2 become 2, 2. Now let us say that this is 2, 3, 2, 3, right? Now it is 1, 2, 2, 3. Now you change this 5, 7. You hold this 1, 2, right? Now I will get 1, 5. 1 is 5. Next this becomes 2 and this becomes 7. So I get a transpose of it. Why transpose is needed? Because that property is used for doing lot of solutions, which we'll see later. I don't prove, right? You don't need proof. Why somebody has proved it? Why you want me to prove again? I don't even want to understand proof. What I want is what is the formula? Tell me what is the formula. I will implement that.
What is one application?
Transpose solutions. Plenty of solutions will come.
You mentioned one rotate.
Pivot. Pivoting. Yeah.
Does it really something like that? You take an image matrix and then we need to take a transpose and review the
Flipping is like that, no? When you try to flip it, you try to do it partially. Right. Basically, it is called data augmentation in image processing. When you augment the data, you try to take the data, you rotate it by 90%, you rotate it by 80%, you rotate it by some angle, right? Then shrink it. All these things will happen. They are nothing but algebraic operations. Right. So once we get the transpose, we would like to look at the properties of transpose, which is not important for us. There are plenty of applications, right? Let us look at how exactly we can do all of this one by one. First, we will do it in list. Once we understand this, we'll go up to possibly inverse. After computing the inverse, we will stop at that, right? Decomposition and inverse we will do, right? Subsequently, we will go for only NumPy. Because the four operations which are very important are number 1 is transpose, number 2 is inverse, number 3 is the dot product, the fourth is Hadamard, the matrix product, right? These operations, once we understand how we do it with that list, right, we can use NumPy directly, because for us NumPy is excellent, right? It's really good. Let's go for NumPy, and before this, let's go for NumPy itself. NumPy documentation. Anything that you would like to read from documentation or read from textbook. Right, NumPy documentation 1.23 manual. Okay, we can go here and we can search for everything. But before that, let us start with how do we do a matrix addition. So matrix operations, right? Matrix addition. Matrix addition. Let us start with the matrix A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, this is my matrix A. Right, now my scalar S is equal to 5. Right, now I would like to compute A. Right, so I will add scalar addition addition to matrix. What is my scalar addition to matrix? What it does, it adds 5 to every element here. What we have done here, it adds 5 to every element here. Right. So now let us take that for let's call B. B is equal to empty list. There is no list, right? It is empty to start with, right? Now I would like to say for value in or for the row in A, right? What I would like to do, not saved. Or not visible. Maybe it has been shared. You can check there. Right, for row in A, what I would like to do, I'd like to create an empty matrix or empty row or empty vector, right? V is equal to nothing. Right, now what I would like to do for everything, right? I had to add the new value for row in A. For every value in the row, right? Now I'm taking this row and I am looping through this row. First I loop through this list, right? Then I loop through this row for row in A, row 1, row 2, row 3. Now for column in row, I will take every column. For column in row, what I would like to do, I will add that, right? V plus S, right? Now my new element, all of this can be Pythonified. We will see that new element. New element is equal to, right, column plus scalar, isn't it? I'm adding each of the values. Now what I would like to do, I would like to say that, okay, you just change this, right? Your V dot append, right? New element, right? Now I would like to just print V, right? Print V. Now let us look at how it is working, right? Now if we look at it, it says that it is adding 5 plus 1, 6, 5 plus 2, 7, 5 plus 3, 8, 6, 7, 8, 9, 10, 11, 12, 13, 14. It is adding each of them. Now I want to add each of this element to B, the new matrix. Getting the point? Are you able to get this? How we got this? Right. Now I would like to add it here. Right. So I will just comment this. Right. I will comment this. And I will say append new element or V. Right. Now I would like to print B. Print B. Same thing, right? Right. We are getting 6, 7, 8, 9, 10, 11, 12, 13, 14. Right. Now I would like to convert this into a function. Now let us say that I would like to say matrix scalar addition, Right. My definition will be, body will be add, right, scalar. What are the inputs to this? I have to send the matrix, I have to send the scalar, right? I will send a matrix and I will send M and S, right? I will take only these two. And now I would like to check this, right? I will keep it here. I will just paste it here. So for row, right? This is not needed because this is already working. It is B append. Right now I have to return B. For row in not A, matrix M. For row in M, for column in row, new element is equal to column plus S, right? Append this, append B. Now what I had to do? I had to return, right? After this, there is a loop. Now I had to return B, right? I had to return B. Now let us check, test scalar addition. Matrix scalar addition, right? Now I would like to, I have A, right? A is already there, right? Let us look at A, right? Let us look at S, right? A is there, S is equal to 3. Now B is equal to add S, add underscore S, A and S. I am passing these two. Now I would like to print two matrices, B. Okay. So this should be S, right? 4, 5, 6, 7, 8, 9, 10, 11, 12. You can check for other numbers. You can try that once. Okay. Now let us create the similar thing in NumPy, right? What I had to do, I had to import NumPy as NP, right? Import NumPy library. Import NumPy library, right? It has been imported. Now A is equal to np dot array, right, of this matrix. This will be given as np dot array. Now B or S is equal to 3. B is equal to A plus 3, right? Print B, right? Are we getting the same answer? Right. In fact, why we limit at the transpose or possibly the determinant and things like that is proved by induction. When 5 are working, should I do everything? No. Now I understood what is to be done. How do I translate any formula that is given to me to a working model? Rather, as a AI engineer, where we are interested in is handling boundary cases, exception handling, error handling, right? These are the things which are from software engineering side I had to add there. Part 1. Part B, can I improve the speed? That's part B. Part C, can I give the insights? Something is happening there. Can I give the insights? Can I convert a business problem into a technical problem and solve it? These are the 3 phases in which you can work on. convert anything, any formula given to you into this. Normally that will be useful for you in PhD. Because most of the time you may not get into writing these algorithms on your own unless you do your research and create new algorithm. It may not be needed, but it is good to know, right? Always you can do that. The second part is now you move from NumPy to Dask. Dask is a programming library where it is multi-threaded and distributed, right? DASK, right? It is pandas and 100 systems, 1000 systems, right? Pandas itself is a NumPy library. Pandas is built on NumPy, right? So Dask is built on pandas or NumPy. So every Dask will contain NumPy below that. So if you know NumPy, if you know pandas, you just have to replace that with Dask, right? So what has been written in scikit-learn using NumPy and pandas, can you redo that with Dask? Can you test it for 200 GB data, right? On a 16 GB machine. When you can do that, yeah, you are done engineering, right? You are done how to work with big data. That is what is expected. Yeah. So this is working. In fact, you can work on subtraction. Can somebody show subtraction? Same thing, change everything. Only this will be changed, right? We'll change only this. Subtract is. We'll make sure that we'll just change subtraction, and this will be scalar subtraction. Right, I do not have to do this, I have to just do this. Right, now this has been done and I would like to test it. So my testing is very clear. Test scalar addition or scalar subtraction. Scalar subtraction. Right, now I have this, I would like to call this as subtract. Right, new matrix is this. So when it is subtracted, -2, -1, 0, 1, 2, 3, 4, 5, 6. We got this. Now we would like to do the same thing with NumPy. Right, we will do everything is same except I would like to make this as minus s. Right, -2, -1, 0, all these things. Yeah. Now actually I can write my own thing here. I will call this as sub s2. Right, now let us write this with NumPy. Right, normally I will import here because it may be imported already. You can check that. I will use this and this will be my right. So this is my b. B is equal to not subtract s. B is equal to a minus s. B is equal to a minus x. A minus s. Right. Return b. Return b. Right. So now I would like to make sure that I will send AB. Yes, return b empty. So return b. So my thing is done now. This is using NumPy. Now I would like to test it. Sorry. Let me call this as S2 because S1 is already there. Right, now I would like to send, right, B is equal to sub S2 A comma S. Right, now print B. Right, now what we have done, we have done three methods. Using the Python list, we have implemented scalar matrix operations, addition and subtraction. Using NumPy, we got the same results. Using NumPy, we wrote our own functions. Right, you can see you should be in a position to move from anywhere to anywhere. That is what is needed. Okay. Because sometimes I prefer you develop your own library using existing libraries. When you want to say profile, you just run one profile command and send the data. Rest of the thing should be done by Python code. You should not be looking, writing. No. When you write it, I feel that you are gym rat. They will go to gym, lift 200 kgs and other things. But you never do that. Why do you want to do that? Functional strength, right? So functional strength is very important. Same thing for us engineers. Fit for use. Anything more than that is good for, kind of speaking about myself, but not useful anywhere. So just focus on what can be done. What are the 3 ways of doing it? If you don't know at least 2 ways, you don't know. Minimum 2 ways you should know. 3 good. Right. Now that's why normally I suggest no H2O, no TensorFlow, no scikit-learn. 3 libraries, same k-means I can do in 3 different ways. Done. You know it. Right. Now remove all of them, write your own function and pass. If it is H2O, H2O code will be called and done. You don't care which library you are attaching. Right? Whether it is PyTorch, whether it is TensorFlow, whether it is scikit-learn, whether it is H2O, whether it is Spark, you should be able to configure. Write those functions and create your library. Only for about 6 algorithms. If you can do that, more than enough. You need not have to depend on anybody. And when you give the code, people will be afraid. What is this guy written? Right. Normally, I don't put it in my JIT because it is for me, not for somebody else. Right. So go for that. Next, we would like to look at matrix addition. How do I add 2 matrices element by element? Isn't it? Let me not go for too much. Let me go for only matrix operations. Right. First of this will be addition. I would like to add. So I will take A is equal to 1, 2, right, comma 3, 4. I will use only 2 elements. Let me not go beyond that. Right. B is equal to 2, 1, 3. Right. Now we have this. Right. So these are my 2 elements. How do I add them? Right. Basically, I would like to add element by element. For that, what I should know? In fact, you can put all the checks. Right? Whether the length of the matrix A is equal to length of the matrix B. If it is not, you should say that addition is not possible. Right? If the length is same, both contain same rows, then you have to check the same number of columns is there in every row or not. You have to check that. Right? We don't do all those things because NumPy handles all those things. Now I assume I have to just write by 2 by 2 ideal thing, how my code should work. How my code should work? I should add 1 plus 2, 2 plus 1, 3 plus 4, 4 plus 3. Right? Now let us add that. Now for element or row in A, right? Or for that row in, let us take row length, right? Row length. What is the row length? Row length is equal to length of A. This is the row length, right? Now let us print the row length and column length. What is the column length? Column length is equal to length of 0. I assume A0, A1, A2, B1, B2, B5, all of them are same. Right? Now I would like to say shape print, right? Or just say shape is equal to row length and column length. This is row length and column length. Print. What is the shape of the matrix? Right? A is a 2 by 2 matrix. B is a 2 by 2 matrix. Now, let us say that I do not want to do this. I would like to do it indefinitely. We'll see that later. Right now, I know it is 2 by 2. I have the row length. I have the column length. Right now, what I would like to do, I would like to add element by element. Add corresponding elements. How do I do that? First, I will print. I will not do anything. First round, I will just try to print for row in range, row length, right? I would like to just print the rows, right? Print a row, just print that, right? It is printing 1, 2, 3, 4. 2 rows have been printed. Yeah. So now, visible? Visible? Yeah. Okay. Able to print it? Now, for every column in the row, I would like to print that. So if I know row column, that becomes a cell. Isn't it? Row and column intersection is a cell. Row, column, for every row, for every column, I am getting the cell. C cell is equal to A cell plus B cell. Isn't it? C row column is equal to A row column plus B row column. That's my addition. Yeah. So now let us implement that. Before implementing this, we would like to implement for column in row. Print column. Right. Though this is a wrong method, right? Integer object. Oh, okay. So row is not okay. A row. So column in range, column length, right? I would like to print a row, right? Column. Right now we can see it is printing 1, 2 as row and 1, 2 as column, 3, 4 as row, 3, 4 as column. The row has been printed and the column has been printed. Now I would like to take this further and I would like to make sure that I take this, right? I would like to add it here, right? How do I do this? For row length, I will not print it, right? For column length, I don't print anything, but rather I would like to create 2 elements. The 2 elements are C is equal to, C is equal to empty list, right? And before this, I would like to create new row. I would like to create new row. These are the 2 data structures I am creating, right? What is my new row now? My new row, right, is I have to add something, right? Now cell, C cell is equal to my A row column right? A row column plus B row column, isn't it? B row column. Now I would like to print C cell. Right? It prints because I'm adding 2. What is the value I'm trying to add? No, 2 plus 1, right? 2 plus 1, 3, 3 plus 1. So let us look at 1, 3, 3, 7, 7, right? So it should give me 3, 3, 7, 7. But what I want, this 3 should come here and should be added as one row. This 7 should come here and should be added as one row, right? For that, I will introduce new row here. I'll introduce new row, right? My new row will be added here. So new row dot append, right? C cell, isn't it? I'm adding C cell. Now what I would like to do, for after all the columns have been done, now I had to add this to C, right? My C equal to, sorry, C append, C dot append is equal to C underscore cell. Right? Now I have to print C. Print C. Oh, sorry. It's not C cell, it is new row. It is new row. Right? Now we got 3, 3, 7, 7. So we did the matrix addition, matrix addition. Now we would like to test this, whether this function works. If I try to do a, let's say that I would like to do this, right? I would like to call this as, okay, I will add it here. I would like to add np array, np dot array, right? This is my array, right? This is my array, right? Now I will add np array here, np dot array, close this and close this, right? My C is equal to A plus B, right? Print C, right? I got 3377, 3377 as expected in my NP array. Yeah. Okay. Done. When first you are able to do it, no problem. Do it slowly. So just digest it. That's what's important. Once it becomes aha, you need not have to return and see whether you remember it or not. You know, right? It's always good if you try to go by the medium. Yeah. Some are fast. Amen, were you able to get it? Zameen there.
Yes, sir.
You're very loud, man.
Sorry.
No problem. The speaker is louder. Even if you whisper, we can hear you. Okay. Dr. Jyoti, are you able to do it? Hello? Oh, it is transcribing. Hello, Dr. Jyoti, are you there? Okay. We don't know.
So are we gonna look into the sparse matrix as well? Like the
Sorry?
sparse matrix.
Ah,
That the way we try to model that thing in the operation side.
operation side remains same for sparse matrix, right? Most of the operations remain same. The only thing is the representation differs in sparse matrix. Sparse matrix will be represented as a dictionary. It will not be maintained as the dense array, but it will be represented as dictionary. Let us say that only 2% of the out of 100, only 2 have value, rest are 0. Should you maintain all the 0, 0, 0, 0 and then 1 and only for 2 places 1, or you can just say 52 and 97 are 1, rest are 0. You're getting the point. Now we have this. Yeah. So it will be represented simply as a dictionary and rest of the operations remain same. There is no change. Okay.
Okay, sir.
Okay. Let's go back. Now we would like to do the matrix subtraction. Let us go with matrix subtraction itself. I would like to call D is equal to A minus B, B minus A because B looks bigger, B minus A, right? Then print D. See, the expectation is 3 minus 2, 3 minus 2, right? 4 minus 3, 4 minus 3, right? Let us see what is the problem here. So we have it 3377, right? So 2 minus 1, 1 minus 2, minus 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1, 2 minus 1, 1 minus 2, 4 minus 3, 3 minus 4, 1 minus 1, 1 minus 1 is what is expected. We are getting 1 minus 1 and 1 minus 1. Right now, let us look at some of the other versions. Basically, we are interested in when it comes to NumPy linear regression. Let us look at Hadamard product. Hadamard product of two matrices. Okay, so Hadamard product basically is I would like to get the product of these two matrices. I have matrix 1, I have matrix 2, and I would like to find the matrix C. Basically, it will be element to element multiplication. Right? So my C1 is equal to A1, B1. Right? My C2 is equal to A2, B2. My C3 is equal to A3, B3. My C4 is equal to A4, B4. Right? Whatever the operation that we have done in addition, we would like to see the same thing, right? Multiplied here, and that will be Hadamard operation. Mostly Hadamard operation will be done when we want to shrink the image or we want to expand the image. Hadamard operation is there. Right? So though we would like to increase pixel and all those things, that comes later because padding and other things has to happen there. Then only we can increase. We cannot just decrease and increase. Right? So those are all engineering operations, but technically it is for compression or it is for elongation. Right? For expansion or elongation or compression. Then the compression, the elongation can happen only in one axis. It can happen diagonally or it can happen vertically. right? How we are doing all those things? It is rectangular matrix which will be multiplied. Hadamard matrix for the rectangular matrix will be taken, right? We can deal with all of those things when you take up the image processing and computer vision technologies. You will get into the depth, but you have to know the basis is algebra. The linear algebra is used there to do any of these things. Yeah.
But the pixel value will change, right? Should be between 0 and 255.
Yes, it will be between 0 and 255.
Multiply it, get a
No, actually color of that will be between 0 and 155. Right. It is not the pixel itself is 253 pixel. Pixel can be 762 by 1260.
No, I'm not talking about the number of pixels. I'm talking about
Color.
But here also the size of the matrix remains same.
Size of the matrix remains
Only
same.
the pixel value will change.
Oh, no. Actually, when you try to expand, you try to pad it. When you give this is your matrix. That's why I told you. Concept is used, but exactly not Hadamard product itself, and we don't try to do it. This is your smaller matrix. Now we have to increase it to bigger one. Or you want to reduce this way, or you want to reduce this way. Right? Normally what we try to do, we try to pad it, then try to see the corresponding elements are mapped and color is given. Color is not going to change. Right? So color remains same. Then what they try to do, they try to go for color saturation. So they have to make sure that the neighboring colors are similar to original matrix. The shrinking and other things is not simple Hadamard matrix which will be exploded and done. So a lot of other operations have to be carried out. One first thing is padding. The second is Hadamard operation itself. The third is the recentering or saturation of the colors. So once you do all those three, you can see some are blurred, some are bright. If we shrink, it becomes sharper. If we try to increase, right, it becomes dull. So you can see that all those operations are carried out.
If we do only Hadamard, what will happen?
It just becomes, it depends on what you are doing Hadamard for. Is it for color? If it is for color, it will be toned. Let us say in this, the color is 0 to 255, or it will be 2 to the power of 255, 16 million colors. Right? When you try to multiply some number with another number, the color range changes. Right? That is called as toning. So when you try to take blue and try to add 255, it becomes black. Right? Depends on what you are doing. Are you doing it on the position? Are you doing it on the color? Are you doing it on orientation? So depending on what you are doing Hadamard operation, the corresponding effect will be there. Right? If you do it only for color, only color will change. It will not shrink. Right? A dark black may become gray, or white may become black, depending on what you are trying to do. Yeah. And it has got not just image compression. It has got lot of things in most of the places, especially when you would like to say that you have A1, A2, A3 and X1, X2, X3. That is set of linear equations. Now, let us say that we have 2x plus 3y is equal to 10, right? 6x plus 4y is equal to 15. This is the set of equations that you have. Right? Now, let us say that I represent as 2, 3, right? 6 and 4. Right? I can go for representing this x and y and go for matrix multiplication, cross product. If it is cross product, it will be 2x plus 3y. 6x plus 4y. I will get the same thing. Or I can represent this as Hadamard operation. Is it same now? If it is Hadamard operation, 2x plus 3y, 6x plus 4y, same thing. Right? Now I may have to do a lot of other operations. We'll see that later because that depends on the application. Mostly engineering applications, right? So a lot of engineering applications are there. We are not much interested unless you go to computer vision and things like that. You write your own library, not needed, right? But Hadamard operation is one of the good operations where the simpler one will be matrix cross product. The same thing can be obtained with cross product. Cross product is nothing but a row is applied here, column is applied, and you will multiply and you will get the same thing, right? This will be represented as Z, a separate column matrix, right? This is your Y, this is your X. So once we get that, in fact, you can see what are the applications. Lossy compression. If you want to compress the image, you can use Hadamard, for example, JPEG, right? You can look at that, right? Deep learning, GRU is nothing but gated recurrent unit. So if you want to get that, you can go for Hadamard operation. So you can go for Hadamard operation, right? There are plenty of applications. You can just read them, right? So, oh, this is your area, antenna arrays, right? If you want to, right, neural networks, right? This is the way neural networks will be formed, right? If you look at the neural networks, they look like this, right? So we have neural networks, right? This is X1, this is X2, right? Now we have two neurons here, Y1 and Y2. This is the hidden layer. Both of them should come here. And finally, we will have this basically is called as an XOR gate, right? So this is nothing but an XOR gate. So if you want to do this, right, this easily solves the XOR problem. Right now, if you want to represent this X1, right, this is W1 and this is W2. This is, let's call it as W11, W12, W21, W22. Right? What we are doing is W11 into X1 plus W12, right? W12, W21 into X2 is your Y1. This is your Y1. Yeah. Right. Similarly, W21, W12 X1 plus W22 X2 is your Y2. Is it similar to this equation? Right? Is it similar to this equation? You can write this as W11, W21, W12, W22 is one matrix, right? Another one is X1, X2, X1, X2 is your another matrix. Can you get the Hadamard product of these two? This is your neural network. And when you get the determinant, this will be W31, W32. Now the output of this will be given as XOR product. You can write this very easily. Yeah.
Almost everything is getting into matrix.
That's why the movie was named as Matrix. That was the original idea behind Matrix, because everything is within this, and somebody is manipulating rows, columns, and other things, and that is the computer was the theme. Okay, so now we did Hadamard product. Sorry. Okay. Thank you. Share the screen. Okay, so now we did this. Now let's go for. Okay, let me call this as. LA session 2, right? You can go to NumPy user guide. You can just say Hadamard. Yeah. So A star B will do, but normally we don't do it. Rarely we use this because there's a much better version of doing.
Is Hadamard product and A star B are same?
A star B are same.
Same.
Yes. Okay. That depends on who is implementing. That's why they had given who has implemented, how they have implemented it, right? In different languages, how they have implemented it. So in programming languages, for example, NumPy, how it has been implemented in NumPy, you can see this. They're just giving NumPy. Okay. NumPy Hadamard. Asha, I mean, yeah, good afternoon, Asha. I mean, session. Oh, yes, yes. Actually, I'll call you by evening.
And once I follow the
Matrix probability.
no,
Can
I just will not let you know where it's playing to get there. So far, probability correct.
go into the
Many of the slide.
Yeah, yeah, sure.
once going the school days.
So multiply. In NumPy, it is multiply.
Okay.
NumPy multiply. You have to just check which is the implementation, what is the syntax for that. We have to just check it and do. Okay, so once that is done, we would like to go for what is called as a transpose. Right, so we did matrix multiplication and okay. So now let's before going to the other things, let's look at some statistics, because statistics and pre-processing are two things that we want to do with our matrix operations, right? So what is statistics? What exactly you would like to see in statistics? What is statistics in the first place? Descriptive statistics for you. If you want to describe something, what is the description? How will you do that?
Data you can arrange.
You do all those things. What is 5-point matrix? 5-point summary.
It's mean, max, median, mode, and count. It's
Okay, 75%, 25%. Right, min max 75%, 25%, 50%. So this is your 5-point summary. So that gives some idea about variance. Right, minimum minus maximum is variance. Right. So once we know what is minimum and maximum, I should know how the shape looks like. Right. So when we look at statistics, basically we are looking at few things which are important for us. Right. I will not get into hypothesis testing and other things which I might have been already. So we are looking at any data that is given to me. I must describe this with two things. The first is shape and range. Right? Normally, the range analysis will be done with mu value and sigma value. Right? Sigma is nothing but standard deviation. Right? Anything that is within plus or minus 1 sigma is 65% if it is normal. Right? Plus or minus 2 sigma will be around 95% if it is normal. right? Plus or minus 3 sigma, it will be about 99.6%, right? If it is normal, right? It means that I have these things, but I really don't know what is the shape of it. Shape of it will tell me which distribution it is. I can fix any distribution as normal. That is what the central limit theorem says. Central limit theorem says when the data is huge, every distribution is a normal distribution. Now let us look at this. Is this a normal distribution? You think so, but actually it is a normal distribution. It is a normal distribution. Because of these outliers, the mean is coming somewhere here. But actually, if you look at it, this is normal distribution. You have to treat the tail part separately. You have to treat the head part separately. Right? Now, this distribution looks like a beta distribution. Actually, it is not beta distribution. That's why central limit theorem says that if the data is large enough, what is large data? If the data is around 300, simply it can be treated as normal distribution. Right? Don't worry about it. That's the beauty of statistics which we are bringing to AI. How many points, data points you need? Minimum 30. If you have 30 points, good to start with. Don't wait for big data and all those things. If 30 points are there, start the work. One variable, 30 point, one outcome, start the work. Less than 30, depend on stats. It is better there. For smaller data, assumptions and things like that, statistics is better. More than 30, you really don't know, it is not fitting any of this, go for AI. Our only problem in statistics is assumptions. If assumptions were not there, we would not have created AI. I have not created AI. My professor's forefathers might have created AI. Maybe Simon Purport, right? John Stevens and others who created Lisp and others, John Chambers, John Stevens and others, they have created AI. So we would like to say, yeah, we are adding something, a dust in it. So we are also adding something, right? For us, statistics is very dangerous. Because it needs minimum 30 people to die before you say it is poison. Yeah, one is enough. One dead, don't eat that. It's a poisonous mushroom. Done. So we generalize it further. Don't eat mushroom. Right. So there is a possibility one of the mushroom may likely to be poisonous, you will die. Don't eat mushroom. Right. It becomes very, very simple for us. AI is always bringing rule of thumb. Now this neural network has taken over and people are afraid. So we are not afraid. For us, in fact, I was doing a project on efficiency. They were building all neural networks and all. Then we found only about 3 rules. Top gear, low speed, efficiency is good. One rule. Whatever the top gear that is possible in that scenario. If it is first gear, second gear, third gear, fourth gear. In the fourth gear, if you drive at 45, fuel efficiency is excellent. That's what data was telling. Why do you need neural network for that? All the 2 GB data has been condensed into one rule. Higher gear, lower speed, efficiency is good. Number 2, when it is up, always run in second gear. People say that no, my car has got a pull, I've got 4-wheel drive. No, irrespective of anything, go in first or second gear. Period. That's what data said. Right, it's good data, IoT data, internet inside. Right, they collected all the data. What data says is during steep things, you just go in second or first gear. Don't try to go in fourth gear, speed and all those things. That is good for Van Diesel and others to go in fast and furious. If you really want to do, because people like me, for us, fuel efficiency is everything. Safety, fuel efficiency. How many airbags are there? If it is not there, how much it costs? 3,000 rupees, put one. At least one, put one. Right, airbag is essential. Next is speed. Right, how is the pickup? Next is fuel efficiency. But actually the other way around. First is fuel efficiency. Right, otherwise who will go for it? 4-wheel drive, 4 km per liter, you keep it. Or somebody else give the money, I will drive it. Right, so we have been tuned, we have been told value for money is more important than show off. There is nothing wrong in show off. But to appreciate him, he has to give me money. Why should I watch a movie and tell movie is good? Give me money. Otherwise, anyway, after some time it comes in OTT or YouTube, somebody will download our Telegram channel, right? So it is not wrong. So people say, no, 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 it is immoral. Come on. You are charging 300 rupees for popcorn inside that stall and you say it is moral. And I download something from Telegram channel and watch it, is it immoral? So who are you to set it? It should be written in our Vedas. Veda is not there, movie is not there in Vedas. So movie is not illegal, not immoral. Done. Is it there in Bible? Hey, is it there in Quran, man? I mean, are you there?
Yes, sir, I'm there.
Is movie is there in Quran?
No, sir.
It is not haram. No problem. We will drop it.
I mean, it's a controversial debate. If you
No, it is not there in Quran. You can watch.
I mean,
It's convenience, man. Don't worry. Okay. So it is very much necessary for us to see anything has to be reduced to rules so that the behavior can be formed. By having neural network, by having hundreds and thousands of rules, the behavior cannot be changed. The behavior can be changed with simple and stupid rules. You just tell this, highest gear, lowest speed, people will drive. And my classifier should tell me, should beep me, I'm not in highest gear for that steep. Normally we call that as load. There is a load for that load. If the torque is not there, it must beep me. If the torque is less and the speed is more, it should beep me. You're going beyond. Enough. Within 30 days, the behavior is created. There is no wheeling, right? There is more fast drives because government needs all those things. In fact, I would like to see which Indian road is capable of having a car which can be driven at 100 km per hour. No road, not even Pune Mumbai highway, right? Because it should be like Nevada desert. It should be at least 100 km stretch. Less than that is not correct. Where is 100 km stretch where you can drive at 100 km per hour? It means that 60 km is enough. Why are you going beyond that? That is statistics. Somebody wants to give more and more and more. Now I heard that Tesla is capable of driving at 250 km per hour. Man, I'm bringing it to Bangalore. Whether I get Tesla or I go with Alto or Maruti 800 doesn't matter. Safe also. Very safe because it is bumper to bumper. There is nothing that you can do. Right? Statistics speaks about the patterns in terms of the shape. This is a shape. The shape is lowest gear, highest gear. So now let us say that these are the 4 gears, highest gears, right? Now this is speed, right? Let's say this is medium speed, right? Low, medium, high, right? If we look at it, at any gear, first gear, second gear, third gear, fourth gear, and maybe fifth gear also, but not reverse gear. So you cannot say what is the minimum speed in reverse gear. So this is a uniform distribution, right? Is this correct? May not be correct. This is not the speed. Now this changes. Now this changes to, this is the minimum speed in second gear. Now this changes. This changes to minimum speed in third gear. This changes to minimum speed in fourth gear. Now, if you see this, this is the curve. This curve is what we are interested in. And this is shape analysis. What is the shape? If instead of giving all those gadgets, if it tells me, if this curve is shown to me, right? And say, you are here, you are bad. Done. You don't need anything else. No beep, no discussion, no internet inside, all those things are not necessary. Just give me this. I'm here or not, right? In fact, this we have to be very careful. So this is the range. Am I within the range or not? I should not be below the range. In fourth gear, I should not be rolling at 20 km per hour. Right? At just because it can reach 60 km per hour in 10 seconds, I should not drive in first gear itself 60 km per hour in sixth gear. Both are wrong, isn't it? Both are wrong. We would like to see below or above. It must give me a warning. and this is the shape analysis, right? And this is the range. What is the speed range, right? So speed range for first gear is this. This is the speed range for first gear. Within this range, if you are there, good. If not, change. Right? Can we do this? Absolutely, we can do this. Do we need AI for this? No. Just IoT data and statistics is more than sufficient. So what is the statistics that we are trying to do? We don't check the shape now. We will try to understand the shape in a different way, right? How do we understand the shape? We try to get median and mean, right? The mean value and median value we would like to see. If the mean and median are at the same place, this is mean, this is median, then it is called as normal distribution. If it is not a normal distribution. Right? Now, I would like to compute some of them. What is the formula? In fact, as I told you, when it comes to linear algebra, we are interested only in formula. What is the formula? What I have to implement? What is the application? I'm least bothered about the proof. I'm bothered about the application. What is the application of this? How do I do this? Right? Now let us look at this. What we are trying to do. Yeah. Oh, it's okay. Okay. Now, given a column, right? What I told you about matrix, every data we try to measure and store it as one column. If it is height, you cannot have height as rows. Height will always be a column. Education will be a column, right? Salary will be a column, right? Temperature is a column, pressure is a column, current is a column. You cannot readjust them. So most of the data we encounter will be stored in column fashion. If you look at any analytic databases, they're all column store databases. Whether you look at Vertica, whether you look at something like K2, whether you look at 10 times, all of them, HBase, all of them are column store databases. SQL Server and all of them are row databases, row store databases. DBMS, there will be an engine which does the query, which stores the data and all those things.
That also, each column will contain only that type of data.
Yes, but it is stored as row.
Stored as
Row. That is not okay. Why storing as row is not okay? Because you want to say select age, right? From table this. Then what it has to do? It has to read every row into the memory, select only that, keep it somewhere, then select only that part and give. Now if you store it as column, what happens? Select column, select only column and give it. At least that is twice faster than row store database. We have seen 10 times performance improvement, right? So normally we work with MongoDB.
Because most of our operations will be on a column, so you need to keep getting a column.
Oh yes.
Okay. But if you store all things in column, then for a particular record you want data. So for a particular person, then
that's why it is a vector. Okay. It is a vector. Vector means if it is 1, 2, 3, 4 up to 10, everything will be 1, 2, 3, 4 up to 10. You cannot change the order. That's why it's a vector. So if you know your name, roll number 57 is 57th record, just go to 57 cell in any column, you will get the row. But rarely we go with rows. Because correlation, you will not find correlation between rows. We try to find correlation between columns, right? Mostly when we try to do k-means and others, in fact, we have found a way to do it in matrix. Most of now everybody is implementing it as matrix. We'll see how everything can be stored as a column store only, right? The reason, the proof is HANA, SAP HANA. HANA is a column store, right? The reason, the performance. Right, it depends on how the vendors promote, but normally we don't listen to vendors. Right, is it open source? Not open source, I don't listen to it. Do whatever you want. If it is an open source, I trust. If it is not in open source, no. Right, in fact, that is one of the problem we had with Professor Strang also. So Professor Strang is the originator of MATLAB. Right. So we said, no, you know that how MATLAB is. How do I know MATLAB is not taking Octave and packing it and giving it to me? Performance improvements are there. That's a different thing. It's a good thing. But for us, if it is not open source, it's not good. Right. So that depends on where you are, what you are doing. You cannot do that because most of the design machines are proprietary. Right. For us, no, software, pen, paper, pencil, system, and open source. Done. We don't need anybody. Give me internet, give me data. We will rock everyone. Right. Otherwise, we have to listen. Whoever pays, we listen to them. But the idea is, I have these columns C1 or A1, A2, A3 or X1, X2, X3, Xn. Now, we have seen what is L1. What is L1? Absolute sum of all the values. Right? How many elements are there? N elements. Length of that will give me. So my mean is calculated by L1 divided by N is my mean. We have computed L1. I will take N length, which is nothing but count how many elements are there, right? The L1 divided by N gives me what is the mean value. Though I don't compute the 25th, 75th and all those things, we can do. That is not a problem, right? In fact, easily we can do where this mean value finds and anything less than this, add all of them, right? And do that. So why should we do it? When NumPy has already implemented and done, how do we do it? We don't do it. So my mu is computed as L1 divided by length. L1 of A divided by length. Right? Now,
Mu is average.
mu is median, average. Yeah, mean. Right? Mean or average, right? I will get the mu. Right? Now, I would like to compute sigma. Sigma will be computed as, first I will do x minus mu. Right? Then I will go for x minus mu whole square. Right? Then I will try to compute variance is equal to x minus mu whole square sigma divided by n. Right? My sigma is equal to root of v, or sigma is equal to sigma x minus mu whole square divided by n to the power of half. This is the formula. Right? What this is trying to signify, right? Basically, if we take this, this is the average line. Right? Now we have first deviation, second deviation, third deviation, fourth deviation, fifth deviation, sixth deviation. You have these deviations. Right? And these deviations squared is basically sum of squared. So we have to penalize. There is a possibility if all of them are there and if I try to add them, there is a possibility the sum may become 0. Right? This sum may become 0. What is the better way to avoid this? Square it. Once you square it, it will be penalized. Anybody who is deviating from the center line is penalized. Right? So if it is this, it will be magnified by this. It is this, it will be magnified by this. Right? 8 8s are 64. 2 2s are 4. Right? Just by changing it, you are changing 8 times. Right? If you are small, you are changing only 2 times. But if you are 16 times, 256, 16 times, you will be penalized. Right? Penalty is proportional to absolute value. And what we are trying to do is square this error and take the average. Right? There is a possibility. Most of the time what happens is if you want to take the average, you have to hold one point. You cannot take the average. With respect to what is the average? With respect to average, it has to be taken. Normally what we try to do is we try to say n minus 1. right? The reason why we would like to say n minus 1 is n is called as degrees of freedom. It is nothing but number of points. If we talk to statistics, they say how many degrees of freedom. If we talk to AI, they say how many rows. N is number of rows. Minus 1. Why minus 1? Because I would like to reduce the number of degrees of freedom. It will be restricted to n minus 1 degrees, not n degrees. Right? The idea is n can be anywhere, right? But 1 point is to be deducted. So n minus 1. So this is the formula we would like to apply. So how do we do this? We'll loop through this. First, we'll compute this, then we will compute this, then we will compute this, then we will compute this. For this, we try to have V sum is equal to V sum plus this diff into diff. We'll go with diff into diff. We can compute V sum. So this is nothing but summation, right? Add up all of them, right? So let us write that. Let's go for it and let's write that. 3:30. So, okay. We'll break for some time. We're taking regular breaks. The moment I go there, I will be pulled in. We'll go.
So break till?
Yes. When are you coming here?
No, I'm asking till when?
By evening?
Break till
No. I'm asking you when you are coming to university.
Sir, right now I'm with my family. So I came to Saudi.
Saudi is not far away from India.
We'll be there, sir. We'll be there soon.
You're not giving concrete answer. You are becoming AI.
yes.
Rule based.
2 days, huh? By Monday.
No, not sir. 23rd I'll be there. Basically, this month. I'll be coming
Okay.
up.
Okay. We'll connect again by 3:45.
Okay.
And more Bachchan, please share.
Yes, sure, sure.
He's paying through loan.
Okay. Okay, we'll start with A is equal to 1, 2, 3, 4. Now I would like to find L1, right? I will say L1 is equal to L1 A, right? My L1 is available, right? Now I'd like to find my mu is equal to L1 divided by length of A, right? Right now I can print my mu, print average is equal to mu, right? Average is 2.5. 1 plus 3 3, 3 plus 3 6, 6 plus 4 10, 10 divided by 4 2.5, right? So we got L1A divided by length of A is equal to mu. That's one of the stats that we wanted to see, right? Because we already written L1. Now we would like to see, now I have the mu. I would like to find the deviation or SD, standard deviation, right? How do we compute standard deviation? I should have one V sum, right? V sum is equal to 0. V sum is equal to 0, right? Sum is equal to 0. Next, I would like to look at the difference. The difference matrix is nothing but matrix minus scalar, right? So matrix minus scalar. So now I would like to look at, but there is a problem. When I go for matrix minus scalar, it just gives me absolute distance. It will not give me squared one. I have to compute the squared distance. Where do I get square distance? L2. Right? Now what I had to do, I had to take my my matrix subtraction from a scalar or scalar subtraction from a matrix and send the new matrix for L2. Can you see the chain? The first thing I will try to do is, right, I will compute A minus S. So this will be equal to D. Right? What this gives me? This gives me X minus mu, X1 minus mu, X2 minus mu, X3 minus mu. Do we get this?
Yep.
Right? We will get this matrix. Now what I want, my variance V sum is equal to L2D. What L2D does? Square plus square plus square. I will get L2. Right? Now I have my L2, V sum is equal to L2D. My sigma is equal to V sum divided by length of A to the power of half. Right? We will redo this. We will take V sum is equal to 0, or we will not V sum V0.
I didn't get correctly this L1 and L2. L1 actually I knew that.
L1, yeah, L1 is sum. L1 is sum. L2 is squared sum. Actually, you are penalizing, right? Normally, what happens? Come in, please.
So, these plus ones.
Hi. Yeah, please. Yeah. So, let us look at how it can help, or what it does in the first place. For this, we have to understand what exactly, like we were discussing this, and I was telling I have A1 x1 plus A2 x2 plus A3 x3 is equal to some y. This is my linear regression. I have this regression, right? Now, this regression with respect to values of x2, x1 and x3, this has got some r. Right? So there is some correlation between x and y, and I would like to know whether it is really good or not. Though it's not a correct measure. You should not depend only on that. Right? The other error that you have to look at is MAPE. This is very, very important. Just going with my R square is very good. My R is 0.9. Still there is a possibility you may have problem because this may have same R as this, right? Which correct, none of them are correctly mapping because this is non-linear. All of them are trying to predict it as a linear thing where the error may be less, but mapping is not less. So always we would like to measure with these two. The third thing will be scatter plot. How good will be my y versus y cap? This is y, this is y cap. If it is almost right, there is no deviation, right? If it is like this, gone case, right? Now to detect this, what we would like to do, we will not take all of them. We will just take this, right? First thing, we would like to start with A1. I will select only A1 and X1. I assume X1 is the only variable which is affecting Y. X2, X3 is not affecting Y. That's the assumption, right? I will build my linear regression with this. Now I will compute my R1. It contains some R1, right? Now,
yeah. What is R1 there actually?
R1 is y minus y cap.
Y minus y, what the difference between expected and the computed. And
divided by x will give you what is the correlation. Right. So once you have the correlation, what we are interested in is I will add one more A2 x2 plus A1 x1. This is equal to y. I assume by adding x2, my error is going to reduce. There are few possibilities, right? When I add x2, the error will reduce or error will increase or the error is not going to change. Right? In that case, R will increase, R will decrease, or R will not change. Right? What happens when R increases? It is a good variable. Adding x2 is adding the value to prediction. Accuracy is becoming better. What happens if adding x is not changing R? Simply I'm telling I have 200 variables, I have to use all of them. That is not a good practice. Right? A good model is always less number of variables. Normally, I give this example. Meow. What is that?
Sound is enough to sleep.
It is cat. 90% of times, unless you know it is me who is making that noise, immediately you will say it is cat. How many data points you wanted to say it is cat? The joke is how many Germans are required to change the bulb? Right? So by adding a new variable, if it is not adding any value, if it is not increasing the predictive accuracy, which is nothing but R square, or it is not reducing error, it is of no use. Drop that variable. By adding this variable, we are making equation complex. We do not want complex equations for two reasons. Complex equations are unstable. Any complex equations. That's why when somebody says that they have got 2 billion, 3 billion parameters and things like that, they are unstable. All of us now know Google's model for face recognition is unstable because they give a black woman and it said it is gorilla. People may say, no, that is not, that's it. No, it is social discrimination. It is social, it is not acceptable. I drop AI. I cannot take such kind of indiscrimination. That is not good. Right? It is unstable. If I knew, if it doesn't know, it should say it doesn't know. That would have solved all the problem. Right? We never touch the boundary cases. When we touch the boundary cases, things becomes better and easier. How do we do that? Reduce the number of variables. In fact, it reminds me of a story. The rabbit was moving around everywhere, jumping, hopping, and very happy, and it was. Then one day it saw a centipede walking slowly but elegantly. I don't know how many of you have seen a centipede walking. Very elegant. You appreciate, don't be afraid of that. Just see that it's very elegant. And rabbit got bored. With 4 legs, I'm doing this. With 100 legs, how can he jump? Then it went to the centipede. It said, how are you doing so gracefully? Centipede said, I don't know. God's gift, I'm doing it. Then rabbit said, no, you can teach that to people, how to be elegant and things like that, right? Look, with 4 legs, I'm not able to monitor. So, okay, how are you walking with 100 legs? Right, it put that thought in the centipede, and next time when the centipede started to move, it started, where is my first leg, where is my second leg, where it is moving, it could not able to move. The reason is, it didn't knew it had legs. The moment it saw 100 legs, 100 variables made the centipede to stagnant, froze, right? And that is called as Miller's law. So Miller's law and Hicks law says that more number of options you give, people get confused. When you say that everybody should wear only kurti or kurta and dhoti, everybody will look like a politician. Right? You look at any politician in India. How rarely I see anybody wearing a full suit or possibly a non. That's why I never recognize myself with them. The reason is they look totally different, alien to us. Right? If they were like Gandhiji, I would have been very happy. So many Gandhis are there, right? Only with a lion cloth. They won't even do that. They have so much of money, but they try to pretend like Gandhi, which is not correct. We respect Gandhi because none of his sons he made rich like others. But that's the reason we respect him. Yeah, he deserved to be called Mahatma. Right? He might have done blunders, that's a different thing, but I am rare to see a person living with loincloth and not making his progenies rich and rule the country unheard. Right? He had that psychological capability to do that. That's one variable. Right? You put all these politicians, they cannot move India. Now, I don't believe any of the politicians. I want data. With Gandhi, I would not have asked. If I was born at that time, I would not have asked that. Gandhiji said, okay, it is like God, we will do. Now, even God says, give me data. Where is it? Right. In fact, that's a joke. No, I bring somebody as Rama and he says, no, you bought somebody from drama company. How can somebody come in blue and with a bow and some arrow and other things? He cannot be Rama. And I bring him like Akshay Kumar, they say, no, it's a movie. Right? So that is not a good thing. So what we would like to see is, by adding these two variables, is my R increasing or decreasing? Right? If it is decreasing, yeah, right? Then I will not add this. Now I will add A2, A3x3 plus A2x2 plus A1x1. This is equal to Y. And I will get R3. Whichever has got the minimum, I will select that particular one as the best model. And this is nothing but L1. Now there is a possibility. This is 2, this is 2.5, this is 3. Pretty difficult to do anything. Now I penalize them. When I penalize them, this becomes 4, this becomes 6.25, this becomes 9, exaggerated. Other than this, there is nothing that is related to L1 and L2. But the reason where we use L1 and L2, right? When we have a large number of records, when we have large number of columns. Right? When large number of columns are there, I would like to use L2 because it will penalize everybody and reduce the number of columns. When the large number of rows are there, it's okay. L1 is okay. I can test all of them and I can go with forward selection and backward elimination. That is the difference between L1 and L2. Otherwise, L1 is L2. When you combine L1 and L2, we call it as elastic net. You can go with one of the three. In fact, if you can refer to H2O, right? H2O is one machine learning software. If you can see that, he gives clearly what is ridge regression, what is lasso regression, and what is elastic net. Right? How they use the ridge regression and other things. Now, once we do this, we would like to find L2. L2 is nothing but A1 square plus A2 square plus A3 square. Right? Now, what is my sigma? Sigma is equal to L2 divided by n minus 1 to the power of half. Isn't it? So that's what, let's code this. Hope it answered your question. Otherwise, we'll visit again. Okay. ಮಾಡಿಲ್ವಾ? Okay, so now standard deviation, I would like to call it as V sum, right? Is equal to, my V sum is equal to, first before V sum, I would like to compute the difference matrix. Diff is equal to my A minus mu or sub 2 sub S. I might have to redo this because that may be wrong. Subtract yes, subtract yes. Let me run this. Subtract yes. I will pass my list. Subtract yes. I will pass my A and my mu. Right? I got my difference. Integer object is not iterable. Scalar subtraction. Okay, we are done for matrix. Now we are trying to do it for here. Okay, let me change this. Right, I will just subtract it. Right, so I will give it as diff is equal to nothing for value in A. Right, I would like to find D is equal to value minus mu. Right, now I would like to add diff dot append mu. Right, now I have the difference. I got the differences. Now what I would like to do, I would like to compute.
So it should be D, right?
Sorry?
Diff dot append D.
Oh, thank you. Diff dot append D. Right. Now I would like to find my, I would like to get V sum is equal to L2 of diff. Right. I got V sum is equal to L2 of diff. We got it. Now we would like to see, right, my SD is equal to V sum divided by length of A minus 1 to the power. Right, I will write power. This 0.5 gives me problem because I had to import np math dot power. So import math. Not power. Right, now we got the ST, print the standard deviation. Print standard deviation is ST. This is the standard deviation. Right, now we can check whether 65% of the points are within first standard deviation. Right, between 1.2 because 2.5 is my new value. Right, so 2.5 1.3, right? 1.3 is 1.2 is one standard deviation, 3.7 is another standard deviation, right? Two standard deviation will be minus 0.1, right? This will be 1.3, which this will be about 5.
Minus or plus 1?
This is minus. 1.2, is it plus? Yeah, plus point. No, 1.3, 1.2,
2.4.
minus 0.1. It is 1.2 minus 1.3. On this side, right? We are moving this side. 1.2 minus 1.3. This is 1.2, right? From here, 1.3. This is 1.3. And from here, 1.3 will be minus 0.1. So this is minus 0.1. This is minus 0.1. Now let us look at our things. So anywhere somewhere here will be 0 and 1, right?
What is 1.3?
1.3 is my standard deviation.
Ah,
Just I rounded it off. I never work with smaller fractions. If possible, I'll keep it as 1 only. Right? So now you look at it. Right? 1, 2, 3, 4. Right? So my 65%, right, of 5 is almost 3.5 values. Right? 3.5 values, I can take it as 4 values. Right? 1, 2, and 3 are within 1.2 and 3.7. Right? 1, right? 2 and 3. We can prove it is working. Right? It's too small because the standard deviation is too small. I mean, the number of points are too small, but the idea is this. How many are covered within 1 standard deviation, 2 standard deviation, 3 standard deviation? Larger the numbers, larger the number of points, it can be treated as normal distribution. Right? Now we can get all of this. Right? Now let us say that, let us try this with Now I would like to go for, let's say, A is equal to numpy dot array 1, 2, 3, 4. Right? Now my mu. Now I would like to see what is there in A. What are the things that I can find in A? Right? I can find a lot of things in A. I can find what is the mean value of A. Right? I can find what is the standard deviation of A. Right? Now let us look at, okay, now I would like to look at print mu is equal to mu, right, is equal to A dot mean, right? Next is SD is equal to A dot STD, right? So mu is equal to 2.5 and ST is equal to, they are not taken n minus 1, right? They are just taken n. Okay, so we can find it using numpy, or we can do it. Generally, we try to go for numpy. So numpy provides both matrix operations for scalar addition, for doing other things. Right? Now let's look at how can we go for the transpose of a matrix. Why transpose is required? Most of the times, if I have 3 by 2 matrix, another 3 by 2 matrix, if I transpose it, it becomes 2 by 3 matrix. Then 3 by 2, 2 by 3 can be multiplied. I will get 3 by 3. So for doing most of such kind of tricks, circus, we need the transpose. The column will be converted to row will be converted to column, right? We can transpose. Let us look at how transpose works with numpy, right? So transpose of a matrix. Right? So now let us say that NP or A is equal to NP dot array, right? 1, 2 5, 4. Right now we have the NP array. Now I would like to say A dot T, which is nothing but the transpose, right? It tells me it holds this, right? 1, 5, 1 and 5, which are the column is transposed. 2 and 4 will become new one. Now let us print this NP array. We will print original array. Original array is equal to A, right? Transposed array is A dot T. That's all. So now we get what is the original array? 1, 2, 5, 4. My transposed array will be 1, 5, 2, 4. Right? We must be in a position to transpose it. This is one of the things that we are interested in. Right? Next, we would like to look at what is called as probably. You can finish this. You can see. You can transpose the array. Okay. Now let us look at how do we multiply, right? So now we would like to get one is that, then we would like to look at matrix multiplication. Right? So NumPy linear algorithms, plenty of things are there, right? So any of these functions, you can look at what you would like to multiply dot product, right? Or you can go for vertical dot product or matrix multiplication, right? You can get all of them, right? And Einstein is basically Einstein summation, which is nothing but your kind of Hadamard, right? The decompositions, the various decompositions. Let us look at the various decompositions, how they work, right? We'll take one by one, and then we should be in a position to resolve some of them. So let's look at what exactly is the matrix multiplication. Now let us take matrix multiplication. So before multiplication, matrix multiplication, let's go for dot. Right? What is dot product? So in fact, if you look at the dot product, right, it's the cost. Let me get the dot product here. Right? So if you look at dot product, what they are trying to tell is what is the projection of this on this, or what is the projection of this on this, how much effect, or what is the magnitude that it affects this. Basically, it will be computed as multiply these two, sum them, you will get that. This is 3 by 1, this is 1 by 3. Multiplication is possible, right? 1 into 4 plus 3 into -2 is -6. 4 minus 6 is -2. -5 into -1 is 5. Right? Plus 5 -2 is 3. Right? So this is the dot product. Normally, the dot product will be represented with the just dot. In fact, we can see how we can do that. So if you can get this, it's already there as dot. Now if you see, there's a dot product. Right? Dot product is a built-in function for any matrix in NumPy. Right? If you want a dot product, you have to send another matrix which is compatible. It checks the compatibility and gives the error. Right? Let us see how do we get the dot product. Let us look at the dot product. Right? So once you practice the dot product, the cross product, then the inverse. From next session onwards, we go on implementing algorithms. We will take k-means algorithm, we take linear regression, logistic regression, SVD, neural network. We will take those algorithms, see their matrix representation instead of for loop representation. We will just see one line, implement everything. Right? And we will work on a couple of projects with that. So with our own, how can we detect littering? In the image, can we do k-means and identify somebody has littered? Right? So once you know your algorithm can detect it, scikit algorithm or a TensorFlow algorithm can do it better. Right? So look from two perspectives. One, you can write that algorithm. Second, you can apply that algorithm. So those are the two perspectives and the skill sets you must be comfortable with. Do I know that algorithm? Can I write that? Yeah, I can write that. Can I write that up to Google's? No. Right. I won't write anything more than some 1,000, 2,000 kind of thing. No. If it has to handle, let the best in the class do that. I will use it. Can I apply? Absolutely. I can apply better than the originator of that algorithm. Right. You should be focusing more towards application side, not on the algorithm development side. Never argue with anybody what is the algorithm, what to develop. I know that algorithm. I have implemented rudimentary algorithm for this. Enough. Application, hundreds. You should know what are the applications and apply in one or two cases. One in business, one in text, one in image, one possibly in voice analysis kind of thing. When you applied in multiple cases, you know you got the hang of it. That's what is needed. Yeah, application side, the algorithm side. Algorithm side, we will do all those things. Application side, do a couple of projects. It will be an extension of what you have done in your machine learning classes. But let's do that with your algorithm rather than the scikit-learn. Right? Your algorithm you do. That's easier. Yeah. Okay, now let's go for my B. Let's see, is there any B? Is it 2 by 2? Yeah. Okay, now I would like to say C is equal to A dot B. Right? Now I would like to print C. Now you can see this is my dot product. Right? Why? I will print all of them. Right? What is A? Print first matrix. First matrix is A. Right? Then second matrix. Second matrix, this is B. Next is print. Next is dot product of first and second matrix. We would like to understand a couple of properties of this dot product. Let us see them. Right? 1, 2, 5, 4 is the first matrix. The second matrix is 2, 1, 4, 3. The third matrix is 10, 7, 26, 17. Now let us look at 2, 1 with respect to 1. Right? So this will be 2 into 1 plus 5 into 2 into 1 plus 2 into 1. So 2 into 1 plus 2 into 1, right? So we get 4, right? So we are scoring all of them. 2 into 1 plus 2 into 1. We are multiplying and we are trying to get the. Sorry, no. 2 into 1, 2 into 1 plus 2 into 5. So it have been 12. What is 17? Okay, let us put it as 1, 2, 5, 4. 1, 2, 5, 4. Next is 2143. 2143. So now this will be multiplied with this. So that will be 2 into 1, 2 plus 4 into 2, 8. 2 is equal to 10. So this is 10. So next, this will be multiplied with this. So this will be 1 into 1, 1 plus 3 into 2 is equal to 7. So this is 10 and 7. Right? Now this is multiplied with this. So this will be 5 into 2 plus 4 into 4. Right? So this will be 10 plus 16, 26. Right? Next one will be 1 into 5 plus 4 into 3 is equal to 17. So my matrix will be 10, 26, 10, 7, 26. Right? So 10, 7, 26, 17. So we got the dot product. Yeah. Okay. Huge. When we talk about singular value decomposition, logistic regression, linear regression, neural network, everywhere we use the formula. So if you see the formula for linear regression, so let us go for linear regression. I think we had linear regression there.
Sir, the previous picture, can you explain the logic?
Which one?
The multiplication and
Adamad explain.
so what picture was there? The going in on this one.
No, this basically is projection. If you look at this, this is nothing but cos theta. Magnitude of A, magnitude of B into cos theta. Cos theta is nothing but, now if you look at it, this will be sin theta. This side is sin theta. So this projection here on this is cos theta. When it is projected like this, that will be A, B into cos theta. And that is the dot product if it is vector. If it is matrix, it is matrix projection on matrix. So the idea is, if you have this matrix, and what is the projection of this matrix on this much. Because your projection is basically, if you try to take like resolution of forces in statics, we have F1 and F2 working like this. What we try to do, vertical forces separated, horizontal forces separated, add them. Right? So what we have done, we have projected them as F1 cos theta, F1 sin theta. So F1 sin theta is vertical projection, F1 cos theta is horizontal projection. Get all the horizontal projections, add them, get all vertical projections, add them. That's what happens to the body. If the body is at rest, both of them are zero. Any force can be acting. Right? Fh is equal to 0, Fv is equal to 0. If Fv is 2, it means that it is moving up, levitated, moved up. If Fh is 2, it is moved along. Right? Normally, we do not want when a car is moving, when a flight is moving and other things, right? Unless the thrust vector is applied, we do not want car to fly. Right? We want a car to do, not even float. That's why we say that for that weight, there is an ideal speed. If we try to go beyond that speed, there is a possibility that it may turn around. Because it cannot handle that speed, that mass cannot handle that speed. The balance for the movement happens at some space. And what is the projection? So if you want to see the projection, add the speed, the momentum, and find what is the projection for balance. So plenty, you take statics, you take electricity, you take electronics, but our interest is only in AI. So AI dot product will be something like this. So if you use this, I'm interested only in this. I do not want to read any of this. Right? I will check all the assumptions later, but how can I implement this? How can I implement this? Okay, let us see how do we implement this. This can be implemented with minimum blah blah blah. Okay. At the end, I would like to do only few things, right? That few thing is this. This is what I would like to do. Right? xt dot product x inverse of that dot product 60 dot product y. That is my beta. Why we need dot product? Because somebody has proved this is what the slope will be. If you want, you can look at the derivation, how they are done and all those things. But as an engineer, I will not be looking at it. Why something has to be round? Because the flow will be smooth. I'm not interested in why flow is smooth, how much pressure will be there and all those things. That is design engineer's problem. For me, if somebody asks how, if you want to make the water flow, how it should be curved. Don't make edged. Water flow will be dangerous there. So such kind of rules, I'm looking only at the rules. This rule is for finding M1, M2, M3, A1, A2, A3. That's nothing but beta. I can find the beta using xt. I can do transpose now. I can take the dot product now. I am not done inverse. We will do inverse. I can take inverse of dot product of xt and x and then impose that with dot product of xt and dot product of y. The entire linear regression equation from the scratch is built only with one line. Right. The only thing that scikit-learn is adding is they are testing all the possible errors, boundary lines. Beta is your slope. So when you say y is equal to mx plus c, you can write this as y is equal to mx plus c. This is nothing but beta. So this can be written as y is equal to beta x plus c. This is the slope. Right. That's the reason we would like to see, can it be matrixed?
This is one variable.
Any number of variables. Doesn't matter. X is a matrix.
There are a lot of variants of the
Okay,
matrix.
so beta also is a matrix.
Okay.
Any number. Right. So if you want to take it to.
Seriously, it is that simple. So just put
Absolutely.
Yes.
Right. Trust me, if you don't understand, don't learn it. If it is not simple, don't learn it. If it is not stupid, don't learn it. The moment you are feeling it is complex, it is scary, don't learn it. Trust me. If it is not simple, if it is not stupid, don't learn it. It is not worth. Right. I never try to learn football, cricket and all those things because I cannot catch even ball. How can I play? When I know it is not simple, I don't learn it. Absolutely. You can open the scikit-learn source code and you can see at some point actual linear regression implementation is one line. Right? Rest of the things is 10 kgs.
Yeah.
Right? Whether the data is correct, whether the file name is correct, whether it is divisible by 0, all the errors are handled. That takes about some 10,000 lines. One line is import numpy, do this.
Put all your data into matrix, map them,
Yeah.
build this equation, and then solve. Just not the function is solving.
That's all. Right? You can do it manually. Whatever we have done manually, we can do that here also using NumPy from scratch. Right? That's very important. It's as simple. Yes, absolutely. It is simple and stupid. Right? If it is not stupid, you have to ask the question. Right? You have to simplify. Because I stupidify everything according to my understanding. If I understand, yeah, got it. Stupid. Good, good, good. If it is not stupid, I'm stupid. Actually, I'm not good enough to understand that topic. I don't have basics. I don't have the intuition to understand that. There is nothing wrong with me or with nothing wrong with the teacher or anything. I'm not ready. So I have to ask stupidify it. Bring it to my level. Right? This is at my level. So I can understand, we can derive it. If they ask me to memorize this and do, that's why I never say all our exams are open book exams. Do whatever you want. The thing is, we would like to test your thinking capability, not your reading capability. Can you think, can you give on the spot solution for the problem instead of memorizing things? Memorizing things you can copy and write. I don't care. But for the problem, that programming problem and others, can you solve? Absolutely, that is what we are looking at. Can you fit this regression line for the data set I given? Good. Right? The moment you do that, I know you are capable of doing it. Then rest of the things are now beautifying it. Fit will be, I will write this inside a fit function. Right? Then using this, I will use predict function and I will predict and I will send it. Right? Rest of the things, if you can do it for 5 algorithms, 200 algorithms are also same. Fit inside something is there. Fit it, then predict it. Find rest of the materials in terms of evaluate. Evaluate is pass the actual data and the predicted data, find what is the confusion matrix, find what is the ME, find what is R square, do everything that is possible. Only 3. If we can write these 3 functions, I feel that yeah, you are getting good grasp of whether you do it with for loop using list, whether you use that using linear algebra is left to you. I prefer linear algebra because simplified. Now he can tell, right? He has written ROC fully, what happens? Now, for me, ROC is nothing but my Adamat product. Right? Scalar vector matrix multiplication, nothing more than that. Isn't it? It's nothing more than that. You have all your ones and zeros. Now you have 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1. All these things are there. On this side, it will be 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, done. Right? Then 2 to the power of 3. Instead of writing all for loop, this is nothing but A dot B. Rank order clustering. We'll derive the same thing like in K-means, in neural network. We'll try to find easier ways. We are lazy. I don't know about you. For me, if you allow me, I want to find superior ways of doing it faster so that I can sleep. Right? Not do work. Yeah.
This all goes back, really gets back long ago, right? The linear regression equation, maybe, I don't know, 200 years old.
No. It's hardly about 100 years old.
100 years.
Yeah.
Okay. Scale.
K-means is 40 years old.
What I'm saying is that this all and matrix multiplication, everything was also by code. Why is that becoming such a hype in AI that linear regression, artificial intelligence?
If you don't create a, who will buy that? I don't see. 25 years back when I did my PhD, I did the same thing. I have not learned anything extra after my PhD. The only thing we are learning is I moved from C to Visual Basic to Python to Java, then to Julia, right? Now Python, blah, blah, blah. Other than language changes, nothing has changed. We learned these 6 algorithms earlier. Same 6 algorithms are there. Derivative of these algorithms, instead of 1 layer neural network, I have 10 layer neural network.
The application of those things is current world problem.
Applications is novel. Every new kid coming out with a PhD from a foreign university is teaching me something. Oh, this data can be looked from this angle also. That is new. Till I die, I may learn that. Same. But the algorithms unlikely to change. Yeah. Okay. Okay. Now let's look at the last part. What exactly is the inverse? Now, if we look at the way we would like to understand the matrix, the first thing that we are interested in is, like I told you, the reciprocal of something. If I multiply that with the, okay, now let us say I have A, right, and take the dot product with A inverse, right? This should give me identity matrix. This should give me identity matrix, right? And this is called as the inverse of A. Right? This is called as inverse of A. For solving any of the problems, we need inverse of a matrix. Right? Now, what is this? For example, I will have 1, 2, and 3, and let's say 1 and 0, and 3 into 0, 0. Right? Now, this may not have any inverse, because for the inverse to be true, the value of A, the determinant of A, the L1 of A, right, should not be equal to 0. If it is equal to 0, there exists no inverse. Then we go for what is called as a pseudo inverse. We will not touch pseudo inverse, but most of the times we build only pseudo inverse. We don't use inverse. Right? Because one of the problem with inverse is, if there is an error, I have to handle that. Why should I handle it? Yeah.
The matrix not having an inverse. What is the problem with the matrix?
They are parallel.
Yeah.
If two lines are parallel,
okay,
right, they will not have a solution. A matrix is nothing but kind of it's a plane. So if two planes are parallel to each other, they never meet. They never meet. Right? What is the meeting that is happening? You are here, and there is one more where it is like this. This point is where they are meeting. Right? Here the product is 0. The determinant is 0. Right? Specifically when we try to go for matrices. When I multiply these two, I may not get anything. But when I multiply this, I will get 0. The projection will become 0. The dot product will become 0. Not exactly 0, it becomes identity matrix.
could you give us an example where this kind of matrix can be resulting in from what kind of data?
Yeah, any data. For example, you have the age, right? Then salary, right? Along with the age, number of dependents, right? Vintage, how long he has been there with the house, and all those things. Now, this is your data, right? You have variable 1, variable 2, variable 3, variable 4. Now, let us say that only 4 records are there. This is a square matrix, but actually you will never find square matrix in AI, right? You will have large number of this, and now I would like to take a pseudo matrix or pseudo inverse of this. If 10,000 records are there, I assume 10,000 are there and compute it.
That's why you call it
Pseudo inverse, right? So why inverse is required? Because inverse is required to find some of the things like the beta coefficients, the slopes. I would like to find slopes. Proofs are there. As I told you, I will never prove. Proof normally I will say look at Wikipedia and the paper which has proved it. You will get this.
So in that, what kind of data will result in?
No, not here. Here, if you try to take the absolute value L2 of this or L1 of this, if it is 0, you can find L1 of this. L1 is nothing but determinant, right?
For example, age is 0, so there is nothing we can do. Is that kind of a situation?
Oh, no. If all of this is same number, if all of this is 0, selection of this is left to symbolic methods. Like tree and others, they will drop this. Neural network doesn't know this is 0, this is 1. It will not do anything. Something wrong. Sorry. Okay, so in neural network kind of thing, they never select. Right, but for neural network, I had to test whether the determinant is 0 or not. Otherwise, I will end up in soup. Or I had to find a pseudo inverse. Right. In all cases, we will try to build using these formulas. When the inverse has to happen, inverse may not exist, but pseudo inverse exists for everything. So that's why we don't go for inverse, we go for pseudo inverse. Yeah.
Sir, why did you say determinant is equal to L1?
Actually, when you say L1 for a vector is sum of everything. Right, but when you take determinant, normally determinant will be computed if you take 1, 2, 3, 1, 2, 3, 1, 2, 3. So determinant of this will be given by 1 into this. Right, so this into this minus this into this, right? 1 into 0. Isn't it? Right, 2 into 3 minus 2 into 3 is 0 plus, right, minus 1 to the power of 1, right? 2 minus 1. So this is n minus 1. This is 1, right? This is n minus 1 is 1 minus 1 is 0, right? And this is 2 minus 1. So this becomes minus 1, right? The formula is I to the power of n minus 1 into this, into determinant of anything other than this. You will just try to take this, this and this. This is 1, this is minus 1, this is 1. Right, now you will take this, you drop this row and this column, drop this column and drop this, don't consider this. Now find 2 into 3, 2 into 3, right, that will be 0. Now minus 1, I will take this, this will become minus 1 into 2 into, I will drop this and I will drop this, 1 minus 3, 2 minus 3. So 2 minus 0 plus 1 into 3 and 1 into 3. 0. Right, I have taken intentionally I have taken this matrix to show there exists 0 for determinant. Right, for the matrix. This is nothing but L1, right? So if you take this, all of this will end up with L1. Basically, L1 is for vector what determinant is for matrix. If it is a matrix, we call it as a determinant. If it is a vector, we call it as L1. So there is no L1 here. This is a matrix. We have to find determinant. So if it is 1, 3, I can find L1. I can find regularization only for a vector. Right? Where the what is the application? I can find only one error, which is a vector. I have y. Y is already known, is label. Y dash is what I predict. Y minus y dash is a vector. This is not a matrix. So I can take L1 for y minus y1. I cannot take the L1 for the matrix. Generally, we call it as regularization is determinant. Find the determinant of that. So L2 determinant is basically a squared error or the squared value of that. Right? Ask more questions. Right? Probably I may not know the answer for a lot of things. You may not be asking. Right? That's okay. Right? Only when you get exposed and when you try, you will come with other problems. Find them. Right? Okay. So let's go for now. We got the inverse. Right? Dot product. Now let us look at the inverse. Screen sharing. Tuck, tuck, tuck. We will go for screen sharing. Okay, so we would like to go for screen sharing. Dot product. Okay, inverse of a matrix. Right. I would like to take a matrix. A is equal to np dot array. Right. 1, 2, 2, 3. Next is 2, 1. Next is 4, 3, 5. So this is my matrix. Right now we would like to go here and find what exactly is my inverse. You can look here, right? Or you can look here itself. So you will find, you will get an inverse also. Dot product. For example, this flatten and other things is where you have numbers and you would like to do one hot encoding. You can flatten them. Right, it will be transposed and you will get all those things. Okay, max min production. Sorry. Oh yes, it may not be in direct one. Yeah, linear algebra. So linear algebra, we have that inner, outer, decompositions, SPD, eigenvector, inverse, linear algebra, inverse of A. Now let us take this, right, and we'll put it here. We'll get an error. It says that there is nothing called as linear algebra. That's okay. So np dot, right, now we got it. So now let me take it as A inverse. Right, A inverse is equal to this. Right, A inverse is equal to this. Now I can print A inverse. A inverse. Right. On the other side, I would like to test A dot A inverse is unit matrix or identity matrix. A dot A inverse. Right. Now you can see 1, 1, 1. Rest of the others are 0. Right. What is the formula? A dot A inverse is equal to identity matrix. Right. Same kind of thing we were trying to do, right? What we were trying to do, we were trying to see xt into x whole to the power of inverse dot x dot transpose x transpose y. This exactly is my linear regression equation. So this can be easily written as x dot t, right, dot x, right, whole dot, right, np linear algorithms dot inverse of this, right, dot x dot t dot y. So it looks big, right? It's a single equation, but we don't write like this. We will make it readable. We will take each of them, split it, then try to do each of them. Then we will try to get it. Right, we'll see this. We will discuss the precondition, post conditions of the project. The way we would like to approach the next sessions will be, we will take k-means, right? Then we will take PCA. Then we will take the singular value decomposition, linear regression, right? Logistic regression and neural networks, right? We'll take 6 algorithms. For each of them, we will deconstruct how it works in actual for loop kind of thing. Right, we don't implement the for loop side of it because that you can read anywhere and you can implement it. We try to understand how we can represent as matrix, right? how we can implement it as matrix. One is matrix representation, another is matrix implementation. So once that is done, I want you to read a CS3 file and convert those values either from pandas or from NumPy. You can read it as text, right? And then implement your k-means, right? And see, compare that with scikit-learn k-means which you learned in your machine learning sessions. So the results may vary, but should not vary too much, right? We would like to see, because k-means is not a stable algorithm where it is not converging at any point. It is NP-hard problem, so there is no universal solution, right? That is okay. So then you can start looking at how do you set a seed, how do you make sure that repeatability is there and all those things. But for me, how linear algebra can be applied for k-means, how we can implement it, how you can run a project using your code, your k-means, right? So let's have those 6-7 different algorithms implemented in linear algebra, and we'll see what is behind SciPy, what is behind scikit-learn, what is behind TensorFlow, right? How it may look like. If you really want to open, rip open and see source code is available, but this is how it works. Even if you are plus or minus 25%, this or that side is okay. Don't worry, but it should be similar. When it is saying 5, it should not say -5, right? Then it is not okay. Yeah. Okay. So I will share this sheet also with everyone.
Why is the universe not real zero? Why
Representation in computer memory.
Okay.
So there is nothing called as pure zero, because everything will be implemented as floating point. Only in GPU it will be implemented as integer. Yeah, thank you. Oh, we want to stop the recording. I will not preparation, reading couple of papers, right? Like